Imagine a flash that, in a matter of seconds, can be brighter than an entire galaxy, and still happen so far away that we'll see only a brief needle prick on our detectors. But if that beam is aimed straight at a planet, it can rewrite its atmosphere, what gamma-ray bursts really are, and why scientists hunt them like cosmic signal flares. Emergency broadcast. 0217 UTC. On the duty shift screens, it's a short line, trigger. A gamma detector in orbit has fired. In everyday life, that word means nothing. But in astronomy, it sounds like a siren, because a trigger is the moment when the universe, for a few seconds, becomes louder than everything else. On another monitor, a curve appears, a sharp spike, and a drop. 1 second, 2, maybe 10. Sometimes a bit longer, but rarely. And here's what matters. This isn't light in the usual sense. Not a light bulb somewhere in space. It's a hit in the harshest band, gamma radiation. The operator presses a button, and automated messages spread across the world. Coordinates of a patch of sky, a rough duration estimate, an energy level. At once an invisible network switches on. Observatories, robotic telescopes, people in night domes, operators in control rooms. Because you can't look at events like this tomorrow. Tomorrow is already too late. The gamma burst itself lasts seconds, and the most valuable part begins after, the afterglow. It exhales energy in X-rays, ultraviolet, optical, radio, and fades fast, like a flare that drops into an ocean of darkness. And right now, scientists are doing what science does best when it has very little time. They're hunting. The most dangerous light? The words gamma-ray burst sound like a disaster movie is about to begin. But let's agree right away. No panic. In most cases, GRBs happen so far away that for Earth, their energy is just data in instruments and a beautiful plot. They're bright there, but safe here. And still they are called among the most powerful phenomena in the universe, not out of love for sensation. The reason is simple. In an extremely short time, seconds or minutes, they can release colossal energy as radiation and particles. Sometimes astronomers use a careful phrase. In apparent brightness, it can be comparable to a galaxy. One important clarification. Usually this doesn't mean the object truly shines in all directions like a galaxy. More often it means if it were radiating equally in all directions. In reality, it shines in a narrow beam, and that's where the main point begins. Not a lamp, a spotlight. A gamma-ray burst, GRB, is a short flash of gamma radiation detected by satellites. But physically, it's almost never a sphere that flared up. It's more like a spotlight fired into space. Imagine a dark stadium. If you turn on a lamp in the middle of the field, light spreads in all directions and everyone gets a little brighter. But if you switch on a spotlight and aim its beam in one direction, inside the beam it's blinding, and everywhere else it stays dark. Gamma-ray bursts are the universe's spotlights. And that's why the word dangerous always comes with a footnote. Dangerous only if the beam is aimed at you. And from that geometry comes sober statistics. There are many such events in the distant universe, but the chance that one of those narrow jets is pointed precisely at Earth is far smaller than dramatic headlines suggest. Now, let's unpack where that spotlight comes from. 2 classes, and why we won't turn them into sensation. There's a convenient classification by duration. Short GRBs, usually less than a couple of seconds. Long GRBs, longer. It's not just stopwatch sorting. Different scenarios sit behind it. Short bursts are often linked to mergers of compact objects. For example, 2 neutron stars, or a neutron star with a black hole. We know such mergers exist, and we've even learned to catch them via gravitational waves. And one famous case showed that a merger can produce a gamma signal too, though not always straight into our face. Long bursts are more often tied to the death of a massive star, core collapse forming a black hole or a neutron star, and launching powerful jets. This scenario is sometimes called a collapsar. The star dies, but not quietly. We won't argue about classification subtleties today. What matters more is the mechanism. In both cases, you get a situation where, in a very small volume, an enormous amount of energy is released. An accretion disk forms, magnetic fields wind up, and part of the matter is shot outward in narrow streams at near light speed. The key word is jet, a bullet of plasma and light. Imagine an ultra-dense engine that doesn't run on fuel the way a rocket does, but runs on gravity. Matter falls into a colossal gravitational well, onto a newborn black hole or an ultra-compact object. It spirals into a disk, heats up, turns into plasma. Magnetic fields, like taut ropes, begin guiding the flow, and part of the energy escapes not as a sphere, but as two narrow streams, up and down from the disk. Inside those streams, particles are accelerated to enormous speeds. The jet is unstable. Shock waves form in it. Internal collisions between faster and slower parts, turbulence. And when conditions align, we see what on instruments looks like a short hit of gamma radiation. Then the jet collides with the surrounding environment, interstellar gas, and the afterglow begins. X-rays, optical, radio, like a fading wave after an explosion. That afterglow is gold for science, because the gamma flash is too brief, too sharp. It says, an event happened, but the afterglow says, here's where, here's how, here's the energy, here's what the environment around it is like. Why? It's considered one of the most powerful phenomena. Now, the listener's question, why do people call GRBs among the most powerful events in the universe? Because it's physics at the edge. Extreme speeds, extreme magnetic fields, the birth of black holes, or the collision of neutron stars, converting mass into energy and radiation with incredible efficiency. But again, power often sounds like everyone gets hit. The right way to think about it is different. It's power in the beam. If such a spotlight were aimed at us and occurred close enough, then yes, the consequences could be serious. And that brings us to the most delicate part of the story. Danger, soberly, without horror. What has to line up for it to affect Earth? For a gamma-ray burst to become a problem for a planet like Earth, several conditions have to coincide at once. One, it has to happen close enough. Close by astronomical standards is not the neighboring star, but also not another galaxy. It's the scale of our galaxy. Thousands of light years, not millions. Two, its jet has to be aimed almost exactly at us. A narrow beam means most events shoot past. 3, its energy and spectrum have to be such that the atmospheric impact is noticeable. A planet is protected by an atmosphere and a magnetosphere, but gamma photons can ionize the upper layers and trigger chemical chains. If all that lines up, effects become possible. Effects scientists discuss as principles, not as tomorrow's scenario. The main idea, gamma radiation ionizes molecules in the upper atmosphere. This produces reactive chemical compounds, in particular, nitrogen oxides that can catalyze ozone destruction. The ozone layer isn't armor against everything, but it is an important ultraviolet filter. If it's severely weakened, more hard UV reaches Earth's surface, stressing biology, especially ocean ecosystems and anything that doesn't like extra ultraviolet. This is not everything instantly burns. It's more like atmospheric chemistry changes for a while and the biosphere takes a heavy hit. There are hypotheses that, in the deep past, such a mechanism could have been one factor in mass extinctions. But that is exactly a hypothesis. In geology, there is rarely a single culprit, and proving this was a GRB is extremely hard. And still the question remains, how realistic is it to end up in the beam? Why it's rare? Most GRBs we observe occur at colossal distances. In other galaxies, billions of light years away. We see them because they're unbelievably bright in gamma rays, but that automatically means they're far. For Earth, the dangerous ones would not be the usual distant events, but rare events inside our galaxy, and with the right beam geometry. And here sober statistics switches on. If such hits happened often and struck Earth regularly, surface life would be far more torn up and unstable than what we observe. So the risk exists as a physical possibility, but it doesn't look like an annual lottery, more like a very rare coincidence over very long timescales. And that's exactly why GRBs are interesting not only as a hazard, but as a unique source of knowledge. We can study stellar deaths, black hole births, and extreme magnetic fields, not by approaching them, but by catching their signals. But to do that, you have to be fast, because the traces fade quickly. Pursuit mode, on. So, we have three facts. The flash lasts seconds. Its danger is in the narrow beam. And science is born in the afterglow, which fades over minutes and hours. And right now, somewhere on the other side of Earth, a robotic telescope is already slewing. It's not looking at the sky. It's chasing a fleeing trace. In the next part, we'll do a report from inside that chase. How satellites even get coordinates if the event lasts seconds. How optical and radio telescopes can be pointed within minutes. Why the afterglow matters more than the gamma flash itself. And how, from that fading light, scientists measure the distance to the catastrophe. Who sees the flash first? We're back on the air. From the ground, you can't see a gamma ray burst with your eyes. Its first viewer is a satellite. In space, spacecraft with gamma detectors stand watch. They don't have lenses in the usual sense. Gamma photons can't be focused by ordinary mirrors the way optical light can. So, the detector works differently. It doesn't draw a picture. It counts hits. How many high-energy photons arrive in a fraction of a second? And here's what matters. The burst isn't a pretty frame. It's sharp statistics. A peak. Like a hammer blow on the sensor. When the peak crosses a threshold, the system says, this is an event. Automation immediately launches a chain. Determine the direction as precisely as possible, and send out the alert. Because after that, the race against time begins. How do you find the source? If it lasted 1 second, the hardest part is figuring out, where was it? There are two approaches and both sound like forensic techniques. Approach 1, wide-angle cameras with coarse resolution. Some instruments see almost the whole sky, but give coordinates with uncertainty. Roughly there. That's already useful. It's like telling patrol units, this neighborhood. Approach 2, rapid follow-up pointing. Some satellites, after a trigger, can quickly turn and look in the same direction in X-rays or ultraviolet, where the afterglow is still alive. And there, in a softer band, you can get much more accurate coordinates, accurate enough for a ground telescope to hit the target. Sometimes another trick helps, triangulation. If the same burst is detected by different spacecraft at different points in the solar system, the signal reaches them with a tiny time difference. Those microseconds become geometry. A probability band appears on the sky, and intersections of bands from different detectors narrow the search area. It's like how, by differences in loudness and delay, you can tell where a door slammed in a big house. A network, waking up, the global alert. Next comes a moment you almost want to show as a montage in headphones. An automated message shoots through scientific channels. Coordinates, time, duration, approximate brightness. It reaches people who are asleep and people whose night is in full swing. Someone in Chile is already opening a dome. Someone in the Canaries switches camera mode. A robot telescope, which doesn't know how to doubt, simply turns its head and starts imaging. Because the afterglow lives by a brutal law. The later you arrive, the less you see. Sometimes it's minutes. The first tens of minutes can decide everything. Make it in time, you get a spectrum and a distance. Miss it, and you're left with only a guess. Afterglow. Why the second part matters more than the first. Now, the listener's main question, why is the afterglow more important than the burst itself? Because the gamma burst is like a camera flash in fog. It says, an event happened, but it doesn't give detail. The afterglow is a footprint in the snow. When the jet breaks out, it doesn't fly through emptiness. It collides with interstellar gas. A shock wave accelerates electrons, magnetic fields intensify, and emission begins in more accessible bands. This radiation writes the story more slowly. It lets us measure the source's precise position on the sky, how fast it fades, a key to geometry and energy, its spectrum, and the spectrum is a passport of distance. And often, which galaxy produced it when everything fades and the burst's home remains. The gamma flash is the siren, the afterglow is the report. How they measure distance, redshift in a single night. When an optical telescope catches the afterglow, the next step is a spectrum. They spread the light into a rainbow and look for lines, characteristic fingerprints of elements and gas. But the main thing isn't the elements themselves. The main thing is the shift of those lines. If an object is far away, the expansion of the universe stretches its light. The lines move toward the red end. That is redshift. And here's what makes a GRB an almost magical tool. It can be so bright that, for a short time, it becomes a beacon across enormous distances. We see bursts from distant galaxies and sometimes from the very early universe, meaning a gamma-ray burst isn't only the death of a star, it's also a flashlight that illuminates the space between us and the source. On its way, the light passes through gas clouds, and those clouds leave their marks in the spectrum. So we study not only the explosion itself, but also the landscape along the line of sight, the intergalactic medium, the chemical makeup of distant epochs. Why it's dangerous only in the beam, plainly and honestly. Let's return to the danger topic, strictly sober. We already said it. A GRB is a spotlight. Now, what does that mean for risk? If the jet is narrow, then most bursts simply aren't looking at Earth. We observe the ones we were lucky to catch in the beam. That's already a sample biased in our direction. And how many events pass by us, we can only estimate from statistics and models. That detail matters for risk psychology. We see bright bursts not because the universe is trying to scare us, but because telescopes notice exactly those spotlights that happen to shine our way. Danger appears if the event is within our galaxy, or comparatively close by astronomical standards. The jet is pointed at us, and the energy is sufficient to noticeably change the chemistry of the upper atmosphere. Let me underline, this is not about a blast wave arriving and knocking down houses. Gamma radiation is photons. They interact with the atmosphere primarily in the upper layers. The impact scenario is chemical and radiative. Ionization, ozone changes, increased ultraviolet at the surface. That can be serious for the biosphere, but it's not a movie about instant apocalypse. The chase continues, dark bursts and a deceptive sky. Sometimes everything goes off script. You point the telescope, and there's nothing. The sky is silent. These events are called dark gamma-ray bursts. When the gamma signal happened, but the optical afterglow is almost absent or too faint. Why? There are several reasons. Dust in the host galaxy can absorb optical light. The burst can be very distant, and visible light slides into the infrared. Or the jet geometry is such that we see the gamma peak, but the optical afterglow is weak, and then the hunt gets smarter. If we don't see it in optical, we search in infrared. If not there, we bring in radio. If we don't have coordinates, we wait for refinement in X-rays. It's a report where the heroes don't sprint down a street. They reconfigure instruments and strategies. GRBs as a laboratory, speed, magnetic fields, the limits of matter. And here, at the core of scientific value, we step from how to catch to why catch. Gamma-ray bursts are a laboratory of extreme physics because at once they combine enormous energies in tiny volumes, plasma at relativistic speeds, magnetic fields that can steer flows of matter, shock waves where particles are accelerated to colossal energies. We can't build such a laboratory on Earth, but we can observe it if we catch the light in time and read it correctly. And again, the afterglow becomes central. From how it fades and what its spectrum looks like, we can estimate how narrow the jet is, how much energy was actually in the beam, what the environment around the source is like, dense or sparse. It's almost cosmic scale forensic work. Reconstruct what happened and how from the traces at the scene. We caught the coordinates, but that's not the answer. Yet, and then, luck. The coordinates are refined. On the images, a point appears that wasn't there yesterday. It fades before your eyes, frame by frame. A spectrum is taken, lines are found, redshift is calculated. And now comes the reporter's strangest feeling. You realize the event has already happened, but its consequences, in the data, are only beginning. Because at this moment, two questions arise that flip the plot. One, what was it? The death of a massive star, or a merger of compact objects? Two, where exactly did it occur? In a bright star-forming region, or on the outskirts of a galaxy, where old systems drifted for a long time before merging? To answer, we need more than coordinates. We need to see the burst's home, its host galaxy, and we need to understand the event's signature. Duration, spectrum, afterglow shape, sometimes a connection to a supernova. This is no longer an emergency broadcast. It's an investigation lasting weeks and months. Afterglow matters more than the burst. But there's one more signal. We're used to thinking there's light, and that's it. But in recent years, science gained another channel. Sometimes space reports such catastrophes not only with photons, sometimes with gravitational waves. And if a burst is tied to a neutron-star merger, we can catch two messages. One, in the bending of space-time, the other, in gamma seconds and the afterglow. When that coincides, events stop being distant flashes. They become points where different physics converges into one. In the next part, the final one, we'll do the main thing. Assemble the two GRB classes into a clear picture without sensationalism. Explain how getting hit by the beam is estimated statistically, and why the risk for Earth is considered low but not zero. And show how GRBs help us understand stellar death, black hole birth, and the history of the universe, and why these seconds, which can be dangerous in theory, have in practice become one of science's best gifts. A case file on the event, short or long, and why that changes everything. We have coordinates, we have a spectrum, the light is fading. Now the studio asks a question that sounds almost dry, but decides everything. Was this a short GRB or a long one? Because those two classes involve different crimes, different locations, different traces. If the burst is short, it's like an emergency clap of ultra-dense matter. Two neutron stars, or a neutron star and a black hole, orbited each other for a long time, losing energy and in the end merged. At the moment of merger, an ultra-compact object is born and jets are launched. In gamma rays, a hit. And then sometimes another important trace appears, a kilonova, a warmer, more Earth-like afterglow, powered by the decay of heavy elements in the ejected material. If the burst is long, it's more like the final act of a massive star. The star burns out from within, the core collapses, and, if conditions fit, a compact object forms and jets launch, punching through the stellar envelope. Long bursts often have an association with a supernova, but you can't always see it, and not immediately. Sometimes it emerges later, once the afterglow fades. This isn't a binary guilty not guilty button. It's two scenarios that help explain why one burst lasts fractions of a second, while another lasts tens of seconds. And the main point, in both scenarios, the key is the jet. Why it's a beam, not a ball, the geometry that saves. If these events radiated equally in all directions, the universe would be very different. And life on planets would be different too. But nature often acts economically. Energy isn't smeared out. It's concentrated into narrow streams. Jets are not just a pretty word. They're a rescue mechanism for everyone who isn't in the beam, because a narrow beam sharply reduces the chance of being hit. And yes, that creates an illusion. We observe bursts precisely when the beam happens to point at us. Because of that, it feels like there are so many, they're everywhere. But in reality, we see only a small fraction, the ones that winked at us with their spotlight. So when someone says brighter than a galaxy, always keep the footnote in mind, brighter in the beam. Multi-messenger, when space speaks two languages. Not long ago, we caught catastrophes only via light, gamma, X-ray, optical, radio. But now, sometimes, a moment happens that science works toward for decades. Gravitational waves, plus there's a gamma ray burst, plus an afterglow. If the event is a neutron-star merger, it can, 1. Bend space-time, and so gravitational wave detectors pick up a signal. 2. Produce a short gamma ooter, if geometry allowed. 3. Flare in optical and infrared as a kilonova. 4. Leave a radio echo for weeks and months. It's like an investigation where you have video, fingerprints, DNA, and eyewitness testimony, all at once. And in those moments, GRBs stop being dots on a plot. They become a laboratory where you can test how jets are born, how narrow they are, how matter is accelerated, and what elements are synthesized in the ejecta. Yes, including heavy ones, the ones that make the world richer than iron. How realistic is it to get hit by the beam? Statistics without scare tactics. Now, the question that needs a sober answer: how realistic is it for Earth to end up in the beam? Let's start with what reduces the risk almost automatically. 1. Most GRBs happen very far away. We see them precisely because they're bright, but brightness doesn't mean closeness. 2. Jets are narrow. Even if an event occurred relatively nearby, the geometric hit chance is small. 3. The source scenarios are rare in our galaxy. Long GRBs are more often tied to very massive stars and special conditions, for example, at rapid rotation and certain properties of the star's chemical makeup and environment. This is more common in certain galaxy types and stellar environments. Short GRBs are merger outcomes. Such systems exist, but mergers are rare and the beam is narrow. What remains? A physical possibility over long spans of time. To speak carefully, the danger zone is a few thousand light years, on the order of a few kiloparsecs, for an event with unfavorable parameters and a direct beam hit. That's not an exact number in the table of fate, but a landmark that shows the scale, inside the galaxy, but not next door. And again, even on that scale, the event still has to be aimed at us. So, the correct risk formulation is not zero, but not everyday life. More like a rare factor on geological timescales than a threat in the next few years. What a nearby GRB could do. Atmospheric chemistry, plain and simple. If we imagine a close, unluckily well-aimed burst, the mechanism of impact doesn't look like flame. It looks like chemistry. Gamma photons enter the upper atmosphere. They ionize molecules, knock out electrons, and trigger chains of reactions. Among the important products are nitrogen compounds, nitrogen oxides, which can accelerate ozone destruction. Ozone isn't a wall, but it is a filter. If it's noticeably reduced, more solar ultraviolet will reach the surface, especially the harsher UVB. That's stress for the biosphere, plankton, plants, anything sensitive to ultraviolet. Could this rewrite atmospheric chemistry? In principle, yes, for a time. Exactly how long and how strongly depends on the event's power, distance, and spectrum. Here models give ranges, not a single number, and again, an important tone. This isn't necessarily the end of life. Life on Earth has endured harsh conditions and can retreat into the deep ocean, into soil, into shelter. But it could be a serious ooter to ecosystems and climate-linked chains. And this is one reason GRBs ended up in discussions of danger. Not because it's convenient for headlines, but because it's a real physical mechanism of impact. Why we learn about a star's death in seconds, the role of watcher satellites. Let's return to the science side, where everything begins without dramatic words. The burst lasts seconds. You don't have time to manually look through a telescope, so you need sentinel satellites. They catch the gamma trigger, estimate the duration, get rough coordinates. Then automation kicks in. A rapid slew to the source in X-rays, dyes, ultraviolet, coordinate refinement, then an alert to Earth. And that's when the magic of modern observing happens. Robots and people around the world catch the afterglow almost the way firefighters catch a blaze location from an alarm signal. That's the pursuit mode our story started with. Why the afterglow matters more than the burst, again, but deeper. The afterglow isn't just a tail. It's a physical stage where the jet interacts with the surrounding medium. From the fade shape you can infer how collimated the jet is, how narrow, how much energy truly went into the beam, the gas density around the source, and sometimes whether we're seeing the event head-on or slightly off-axis. Sometimes light curves show breaks, moments when the fading rate changes. That can be interpreted as a geometric effect. The jet spreads, and we begin to see its edges. Those details are the key to moving from guessing to measuring. And it's from those measurements that sober statistics emerges, and a sober risk estimate. The danger is conditional, the benefit is real and huge. Now comes the report's main turn. Yes, in theory, a nearby on-axis GRB could be an unpleasant factor for the atmosphere. But in reality, what we observe is mostly distant events. And for us, they're not a threat. They're an instrument. GRBs are a way to study how massive stars die and how black holes are born, a way to study neutron-star mergers and the origin of heavy elements, a way to look into the early universe. A bright beacon lights up gas along the path and leaves spectral fingerprints. So, the most dangerous light also becomes one of the most useful for understanding extreme physics. And we have one last step, the final one, to assemble everything into a clear conclusion. What makes GRBs the most powerful? Why the risk to Earth is low? And why these seconds of light are a chance for science? Final assembly. What makes GRBs so powerful? Back to the listener's core question. Why are GRBs considered among the most powerful events? Because it's a rare case where the universe does three things at once. 1. Compresses colossal energy in time, seconds instead of thousands of years. 2. Concentrates it into a narrow beam, not a sphere, but a spotlight. 3. Accelerates matter to relativistic speeds, almost to the speed of light. If the energy were smeared out in all directions, we wouldn't see bursts from the far side of the universe. But spotlight geometry makes them visible across distances, and makes us random witnesses to those moments when the beam points right at us. That's why GRBs are like signal flares in space. They ignite, shout in gamma rays, and vanish, leaving an afterglow you can study until it fades. Danger without panic. What has to happen for Earth to be truly affected? Now. Honestly about risk. For a GRB to become a serious factor for Earth, several conditions must line up. The event must be close enough, within the scale of our galaxy, not cosmological distances. The jet must be aimed almost directly at Earth. The radiation parameters must be such that they produce strong ionization in the upper atmosphere and set off chemical chains. Even if an event happened in our galaxy, most of the time the beam would point anywhere but at us. And more importantly, most GRBs we observe are extremely far away. They're impressive, but energetically they don't come close to Earth strongly enough to be a threat. So, the right emotional formula is, this is a real physical possibility, but an extremely rare combination of conditions. Not zero, because the universe can do rare things, but not wait for it tomorrow, because statistics and geometry work in our favor. If a hit were close, what it would look like in principles. It's worth repeating one more time. This is not about a blast wave arriving and destroying cities. Gamma radiation is light, photons. They interact primarily with the upper atmosphere. The impact scenario is chemical. Ionization of molecules, formation of reactive compounds, for example, nitrogen oxides, accelerated destruction of part of the ozone, increased ultraviolet load at the surface. That could be a serious stressor for ecosystems, especially in oceans and on land in exposed regions where organisms are sensitive to UV. But it's not necessarily erasing life. Life can hide. Deep ocean, soil, shade, adaptations. So, the more accurate picture is a possible hit to the biosphere and food webs, on the scale of years and decades, not in 1 second it all ends. A chance for science. Why GRBs are a laboratory we can't build. Now, the most important thing, why this whole report isn't only about danger. GRBs are a laboratory of extreme physics. In a single event we see the birth or formation of a black hole, the operation of an accretion disk, jets launched by magnetic fields, particle acceleration, shock waves, interaction with the interstellar medium. We can't build this on Earth. We can only observe it and build models that are tested by data. And in this sense, the afterglow is the main source of truth. It lasts long enough for us to measure the spectrum, jet geometry, surrounding gas density, and sometimes even the structure of magnetic fields. GRBs as a beacon into the universe's history. There's another bonus that makes GRBs special. They shine so brightly that they're visible across huge distances. Sometimes they're used as a flashlight that backlights the universe in transmission. The light travels to us through intergalactic gas and clouds we otherwise couldn't read so clearly. From the afterglow spectrum, we can study the chemical composition of distant epochs, the distribution of gas along the line of sight, how environments around galaxies evolved. So, an event that was the death of one star or the merger of two ultra-dense objects becomes a tool for probing enormous scales. That's science's paradox. What's most destructive for the source becomes most informative for the observer. Final shot, a siren that teaches us to listen. Let's return to the beginning, to the word trigger on the screen. That trigger isn't the horror story. It's the moment when the universe sends a signal. Look here, something rare is happening. Scientists switch on pursuit mode because they have only minutes to catch the afterglow. And if they succeed, years of understanding are born out of seconds. A gamma ray burst is the harshest light we can catch from the sky. In theory, potentially dangerous if the rarest conditions align. In practice, one of the best sources of knowledge about the most extreme stellar finales. And maybe the most beautiful thought here is this. We live in a world where space can be terrifying in what it's capable of, but useful in what it tells us. Seconds of light. And we learn how black holes are born, how neutron stars merge, how jets work, and what the universe looked like when it was younger. That's where our report ends. If you want more stories like this about the most extreme events in the universe, subscribe to the channel. Here we explain space in plain language, but strictly by real science, with adventure and tension. Hit the bell so you don't miss the next episode.